Hello, this is Math 2115 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled More Proofs by Mathematical Induction. In this part of the lecture, we prove that math induction can be used to prove inequalities, things about sequences, and even about geometry, and the list goes on and on and on. So let's talk about proving an inequality. So suppose I were asking you to use mathematical induction to prove that for each integer bigger than or equal to 3, 2n plus 1 is less than 2 to the n. Well, in this case, the property p of n is this statement just using n. Now, the basis statement is the lowest number here, so that is substituting n to be 3. And the supposition for the inductive step, pk, is assume it's true for k, n equal k. So this is going to be 2k plus 1 less than 2k. That is your inductive hypothesis. And the conclusion to be shown is that it's true for n equal k plus 1. So here I'm substituting k plus 1 in for n in the statement. With that as background, I would like for you to give this a go. You know what to do. Prove this by math induction. Let's see how you did. Well, first you have to show p of 3 is true. So you plug in 3 in there for n, and you end up saying 7 has to be less than 8, and you say yes it is, so p of 3 is true. Now you have to show that for k greater than or equal to 3, if we assume p of k is true, then p of k plus 1 is also true. So this is your inductive hypothesis. You assume that this is true for k, and you must show that it is true for k plus 1. That is, we must show that 2 parentheses k plus 1 is less than 2 parentheses k plus 1. And that is the conclusion of the what you have to show. Okay, so you start with this, and you distribute the 2, and so you have 2k, then you have this 1, and then you have another 2 from that one. It is organized a little bit funny. Okay, but that is just doing algebra. That's an equality. But then we're going to say that this part is less than 2 to the k by our induction hypothesis. And 2 is certainly less than 2 to the k if k is bigger than 3. And this is, you've got one 2k here and another 2k here, so you have two 2k's, so there's 2 times 2k, but this is 2 to the 1 times 2 to the k, and properties of exponents say that is 2k plus 1. So by the transitivity of this less than, this is true. Here's a problem about a sequence. So you're saying A1, A2, A3, dot, dot, dot is defined recursively in this way, that A1 is equal to 2, AK is equal to 5 times the previous thing in the sequence. So it's 5 times AK minus 1 for every integer k being bigger than or equal to 2. So you're to do two things. You're to write the first 4 terms of the sequence, and then you're to show by induction a sub n is equal to 2 times 5n minus 1. Prove this is true using math induction. You know what to do. Let's see how you did. Well, the first part was part A, and that's just going to be 2, 10, 50, and 250. So those are the first 4 terms of the sequence. But you're also supposed to prove this by induction. So here is your p of n. You have to show that this is true. And so our base case is p1. And so p1, we let n be 1. And that says a1 is 2. And since that is what we had, P1 is true. Now you have to show for each integer k bigger than 1, if we assume that this is true, P of k, then P of k plus 1 is also true. So our induction hypothesis is we're going to assume that AK is equal to 2 times 5, and that is k minus 1. And what we must show is that pk plus 1 is true. That is, we must show that ak plus 1 is equal to 2 times 5, that is k plus 1 minus 1. Or equivalently, you see we add and subtract a 1, so that is ak plus 1 is equal to 2 times 5k. So let's start with this. So a sub k plus 1 is equal to 5 times ak plus 1 minus 1. But we saw that this was equal to 5 times ak, since k plus 1 minus 1 is equal to k. That's just what we did up here. But then this is the same thing as 5 times, and then we're going to, on a sub k, we're going to use our inductive hypothesis. And so we can say ak is actually this part right here. But then I'm going to reorganize this and move the 5 inside, so that is 5 times 5k minus 1. That's 5 to the 1 times 5k minus 1, and that is 2 times 5k, which is what we needed to show. We're going to talk about a geometry problem now. The word polomino is a generalization of dominoes, and this was introduced by Solomon Golem when he was a 22-year-old university student. He was much older than that, but when I was a 22-year-old university student, he was one of my professors. Subsequently, he and others proved many interesting properties about these polominoes, and they became the basis for a popular computer game called Tetris. My wife used to love to play Tetris. A particular type of polynomial is called a trinomial, and it's made up of 3 attached squares, and they can either look like this, they're straight, or they're L-shaped. And so you talk about having a checkerboard. Call a checkerboard that is formed by using m squares on a side, and it ends up being an m by n checkerboard. Observe that if one square is removed from a 4 by 4 checkerboard, the remaining squares can be covered by L-shaped trinomials, okay, like that. And this is called a tiling of that. In his first article about these, he included a proof of the following theorem, and it's a good example of using geometry and math induction. And so here is what he said. For any integer greater than or equal to 1, if one square is removed from a 2n by 2n checkerboard, the remaining squares can be completely covered by an L-shaped trinomials. Now this is an example of a more general math problem called tiling. So let's talk a little bit about his proof. The main insight leading to his proof is the observation that 2 to the k plus 1 is 2 to the 1 times 2 to the k, and when a 2 to the k plus 1 times 2 to the k plus 1 board is split in half, both vertically and horizontally, each half will have length 2k, so the resulting quadrant will be a 2k times 2k checkerboard. Okay, so here we go. We're going to let P of n be the sentence. If any square is removed from a 2 to the n times 2 to the n checkerboard, then remaining squares can be completely covered by L-shaped trinomials. And that is the statement P of n. So let's start with P of 1. Well, that's a 2 by 2 checkerboard, and certainly if you remove one square, you can, and it doesn't matter what square it is, you can cover this with an L-shaped piece. Now, we're supposed to show for every integer k greater than or equal to 1, if piece of k is true, then piece of k plus 1 is true. Now that means you're supposing the piece of k is true for a particular but arbitrarily chosen k bigger than or equal to 3. And so we're supposing that if any square is removed from a 2k by 2k checkerboard, then the remaining squares can be completely covered by L-shaped pieces. So that's your inductive hypothesis. But now we're looking at what we need to prove. And so, if any square is removed from a 2k plus 1 by 2k plus 1 checkerboard, this is the p k plus 1, then the remaining squares can be covered completely by L-shaped pieces. Okay, so here is the insight that we said. So if this is 2k plus 1 by 2k plus 1, then I have 2k, 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 2k. So I have 4 pieces that are all covered by the induction hypothesis. So these, and we're removing one square. Just suppose we remove a square from here. Then what happens is, and we also remove a square from these, but we remove this square, and this square. So if we move those squares, what that means is there's an L-shaped piece that can cover those holes. And so the rest of this one, and this one can be covered by L-shaped pieces. There's another L-shaped piece, and this little piece up here is also of size 2k, 2k plus 1, so L-shapes cover that all except for that one piece. So you see, we really have proven this by math induction. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless y'all.